All right, you're about to encounter some big boy integration. You already know how to do integration by hand, and this technique called U substitution is just one of many different techniques that you can use when integration by hand fails you. So let's start off with this thought process. You're presented with this integral problem, and you know your very first step is to do your antiderivative and then plug in the limits of integration after that. But you look at that and you say, there's no way in 37 million years I could come up with the antiderivative of that big mess. When you think you can't come up with the antiderivative, it may be that U substitution is the way to go, and that's the case here. So I take this same problem and I'm going to walk you through this complicated U substitution process. It seems complicated at first, and then after you practice it, it becomes more and more routine. So don't be intimidated by the first walkthrough. All right. In the beginning, just take my word on what I'm doing, and then I'll explain why. I start off, I look at this problem and I say, there's no way I can do that antiderivative, so I'm going to go U substitution. So I look inside the integrand, and my most important choice on this whole problem is, what inside this integrand can I call the U? That's my U. Some people say it doesn't look like a U, but that's my U. So that is huge, a huge decision. And I decided that x to the third plus 5 was going to be my U. Now I could have decided other things, like I could have decided U equals 3x squared. Would have turned out to be a bad decision. I could have decided that U equals x to the third. That would have been a bad decision. There's a lot of different things from in here that I could have called U. Later on I'll tell you why I chose that one. So you're taking me at my word. I choose that. And then I continue on. I take that U and I take its derivative, the derivative of U with respect to x. Then Leibniz, remember, told us that we're allowed to move his symbolism, so I moved the dx over there and I eventually solved for dx. This whole thing right here, predicated on my decision for U, is what I'm going to call my substitution bubble. From in here, I get to substitute back into here. So here's what I do. The 3x squared, as I look through here, doesn't really have a perfect substitute, but the x to the third plus 5 does. X to the third plus 5 can be replaced with a U. The dx can be replaced with du divided by 3x squared. The 3x squared, I'm not going to substitute anything in for it, but realize that what's happened is I've taken something that had begun in the x world, and by using things from my substitution bubble, I'm now changing what that problem looks like. Here's what makes me really happy about this. This looks like a mess, but notice this 3x squared in the denominator. I'm going to use pencil, not that pencil. This 3x squared in the denominator cancels with the 3x squared up here. And by doing so, I end up with this really simple looking integral. So I went from there to there. Now let's backtrack a second. See my limits of integration, -1 and 1? Over here they've turned into asterisks. So what the heck? Here's what. The -1 and the 1, remember, they have a relationship with the dx. They say, I'm going to travel along the x-axis from -1 to 1. As I travel along to this step and this step, notice that I no longer have x as my variable. I have u as my variable. So these limits of integration, which had allegiance to the x, now will not have allegiance to the u. I need new limits of integration that pertain to the u. So that's why I put the asterisk there, because I know I can't use the x. All right, so I've done a lot of work to get to here. Now I just do the same old integration by hand that I'm used to. From here, I've rewritten an eyeball adjustment because I know I need to take the antiderivative, and the square root of u is tough, but u to the 1/2 is not. From here to here, I've taken the antiderivative. That's exactly what we do when we do integration by hand. So this is the antiderivative of that. But you'll notice now that I have new limits of integration. So how did those come about? Here's how. Since I was in the u world, no longer in the x world, I have to take my x limit of integration, the 1, and plug it into this equation. Take that 1 cubed plus 5 gives me 6. In other words, I plug in an x, I get out a u of 6. So what used to be an x equals 1 is now a u equals 6 because I'm in the u world. This is an x of -1. -1 cubed is -1 plus 5 is 4. So the -1 in the x world turns into a 4 in the u world. Antiderivative, new limits of integration, plug them in, and that looks like a mess. I've converted it to here. For the purposes of this video, if you're not sure how this turned into 16/3, let's not worry about that right now. You can ask me later if it's a big deal. And this was not going to convert easily, so I just left it as is. All right, so the first time through, that should be a very, very difficult procedure because you've never seen it before. And I also told you that I would eventually tell you why I chose u equals x to the 3rd plus 5. Here's why. As you look in your integrand and you realize you're going to use u substitution, your major decision to pick u hinges on this thought. What u can I pick from in here that has a derivative that's likely to cancel out something else from the integrand? When I chose x to the 3rd plus 5, I was looking ahead knowing its derivative was 3x squared, and I thought the 3x squared would eventually cancel out this 3x squared, which it did. If I chose u to be 3x squared, its derivative is 6x. I don't see a 6x that will cancel here. If I see a u of x to the 3rd power, its derivative is 3x squared, which will cancel this out, but I still have this pesky plus 5 hanging around there. So this was chosen because its derivative would cancel that out, and it made this entire piece u. Choosing the u wisely is going to take some trial and error and practice, which is why the diligent students do their homework. All right, we're going to do another problem. So you would start out looking at this problem. And your first thought is, can I do the antiderivative just by raw brain power? If I can, then I do integration by hand. More than likely you cannot, although there's a few of you freaks out there who can see the antiderivative just by daydreaming. Since I know I can't do it by hand, for most people, I choose u substitution, which means I have to look in here and say, is there something I can call u that has a derivative that will cancel out something else? X squared has a derivative of 2x, and I believe the 2x, the x part, will help cancel out that. Remember, it takes some practice to get used to this, but this is going to be a good u. I go ahead and go through these steps. So now my integration bubble, my substitution bubble will allow me to start changing how this problem looks. Cosine of x squared becomes cosine of u. I leave the x alone because I don't see a perfect substitute. The dx always will have a perfect substitute. And now what happens is this x in the denominator and this x in the numerator cancel, leaving me with an integrand that is totally in the u variable world. If this wouldn't work out where I just had u's for my variable, then I would know I've chosen a bad u choice and I go back and start again. Just like earlier in the previous problem, if I wouldn't have got this canceling and then just u's for my variable, that would have meant I chose a bad u and I need to go choose another one, or I screwed up somewhere else in the process. Okay, back down here. I've now converted to the u world. These are x limits of integration, so I take an x equals square root of pi, plug it in, and get a new u. Take an x equals 0, plug it in, get a new u. And then from there, it's simply antiderivative, plug in my limits of integration, and plow through to an answer. U substitution is taking something that we couldn't do integration by hand with, and eventually turning it into a more simple problem via calculus trickery, and now we can do integration by hand. I'm going to show you one more problem here. Okay, so you see a new problem set up there. One of the things you're going to notice is it has no limits of integration. When you get an integral problem with no limits of integration, remember that it just means, can you please find the antiderivative of this mess? That's called an indefinite integral. It doesn't have a defined numerical answer. So all you're doing is finding the antiderivative. Well, can your brain look at this and figure out an antiderivative? For a few of you, yes. For most of us out there, no. So when you can't do that, you have to think of a U substitution, and the thinking is, what can I call U so that hopefully it cancels out something else in the problem? So I chose sine of x plus 2 for my u because I know its derivative is cosine. Cosine is likely to cancel that out. I always have to verify because the algebra may not work out. Here is my substitution bubble. I start to substitute and I notice that I get the canceling that I was hoping for, which leaves me a very simple integral problem. Well, I can do that by hand easily. Antiderivative plus c, and now, since I'm trying to find the antiderivative of this thing that it has x, or this integrand that's using x, I replace my u back into the x world. So this antiderivative, u becomes that, and now I have my antiderivative in the x world. If you were wondering about this, remember one of the things I have always said is, when you get an antiderivative, wipe your brain clean, take its derivative, and see if you end up back where you started. So I'm going to do that. 2 times 1/2 is 1. Lower the exponent by 1. I have a ninja situation here. I have a function living inside a 1/2 blah 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 squared function. So the ninja is cosine of x, because the derivative of sine x plus 2 is cosine. The derivative of c is just a number, so that's 0. So this is really sine of x plus 2 times cosine of x. which is the original problem. So I know I've lost the screen there, but you see it, so math checks out. All right, U substitution, kind of complicated in the beginning. When you practice the problems, you start to feel very comfortable with the procedure.